Today, your kidneys will filter 180 liters of fluid.
Yeah, 180 liters. It's a staggering number.
Right. And, unless you are wildly mistaken about your daily habits, you aren't peeing out anywhere near 180 liters a day.
No, I mean, you definitely aren't.
So clearly, this massive logistical miracle is happening behind the scenes. Welcome to the deep dive. Today, we're looking directly at you, taking you inside the absolute marvel of molecular engineering, sitting right there on either side of your spine.
Yeah, we are cutting through all that heavy medical terminology to really understand how your kidneys manage this microscopic recycling plant.
Exactly. A plant that literally runs every single minute of your life.
What's fascinating here is that to understand where all that fluid goes, you have to look at the fundamental equation of urine formation.
Right. The math behind it all.
Exactly. It comes down to a really simple mathematical reality. Excretion equals filtration minus reabsorption plus secretion.
Okay, so filtration is that initial 180 liters, right?
Yeah, and that initial filtration is just this massive blunt force process. I mean, it is relatively non-selective.
It just pushes everything out.
Basically, yeah. Essentially, all the solutes in your blood plasma, with the exception of large proteins, obviously, are just shoved out of your bloodstream.
Shoved through that microscopic knot of leaky blood vessels, the glomerulus.
You got it. Out of the glomerulus and straight into a series of tubes. But tubular reabsorption, the act of pulling the good stuff out of those tubes and back into the blood, that is highly selective.
And thank goodness, because that selectivity is literally the only thing keeping us alive and hydrated.
Oh, absolutely.
I mean, the math on this gets terrifying very quickly.
Yeah.
If your kidney's reabsorption efficiency dropped by just like 10%, your urine volume wouldn't just creep up slightly.
No, it would skyrocket.
It would jump from a normal 1.5 liters to over 19 liters a day.
19 liters.
Yeah, you would be losing fluid faster than you could possibly drink it.
Which brings us to the underlying strategy of the kidney. And honestly, it seems completely counterintuitive at first glance.
It really does. Like, why filter out 180 liters of fluid only to turn around and immediately reabsorb over 99% of it?
Right. It sounds like a terrible waste of energy.
I was actually thinking about this biological strategy earlier. It's like, imagine deciding to clean your house, right?
Okay, I'm with you.
But instead of just taking the trash bags to the curb, you empty your entire house, like your couch, your TV, your fridge, the actual garbage. You throw it all out onto the front lawn every single morning.
Just everything on the lawn.
Exactly. That's the filtration part. Then you painstakingly carry only the items you actually want to keep back inside the house.
Leaving the junk behind.
Right. That's reabsorption. Whatever is left on the lawn just gets hauled away to the dump, which is excretion.
It sounds incredibly inefficient when you put it like that. But strategically, it is actually brilliant for biological homeostasis.
Wait, really? How is throwing my couch on the lawn brilliant?
Well, by operating this way, your body doesn't need to build a specific sensor for every single novel toxin or waste product you might encounter in your environment.
Oh, I see. It doesn't have to recognize the bad stuff.
Exactly. It just kicks everything out by default. And then it uses specialized, independent transport mechanisms to retrieve exactly what it knows it needs.
It just carries the couch and the TV back inside.
Yeah, meaning the body actively keeps 100% of filtered glucose and amino acids. It brings back, about 99.4% of the sodium.
But it leaves the trash.
Right. It only carries back 50% of the urea, for example. And it leaves 100% of the creatinine on the lawn to be thrown away entirely.
Okay, let's unpack this for a second. If the body is pulling these specific molecules back inside the house against a concentration gradient, we can't just rely on passive diffusion, right?
No, passive diffusion won't work here.
Because you can't just open the door and wait for sodium to casually float back into the blood if the concentration is already higher inside.
Right. Water flows downhill, but this is like pushing water uphill. There has to be an energy source actively shoving it out of the cellular machinery.
So where does the power come from?
That power comes from the primary active transport system. Specifically, we're talking about the sodium-potassium AT-PACE pump.
Ah, the classic biological pump.
Exactly. These pumps are located on the basolateral side of the tubular cells.
Which is basically the back door of the cell, the side that directly faces the bloodstream.
Yeah, the back door. So they use energy from ATP to physically grab sodium ions from inside the cell and literally force them out into the blood.
Pushing them out the back door.
Right, while simultaneously pulling potassium in.
Okay, so by constantly kicking sodium out the back door into the blood, The inside of the cell develops a severe sodium deficit.
Exactly, a huge deficit.
And because of this specific ion exchange, doesn't the cell also develop a negative electrical charge?
It does. It sits at about negative 70 millivolts.
Wow. So you've essentially created this highly charged, low-sodium vacuum inside the cell.
And the kidney capitalizes on that vacuum immediately. Out in the tubular lumen, the front yard basically, where all that filtered fluid is flowing, sodium concentration is still really high.
And sodium carries a positive charge.
Right. So that positive sodium out in the front yard is desperate to rush into the negatively charged, low-sodium environment of the cell.
It's just getting sucked right in.
Exactly. And this sets up secondary active transport. The cell creates a system where other molecules can, just piggyback on the energy of that rushing sodium.
Well, that's clever.
Very clever. Specific carrier proteins on the brush border, those microscopic fingers on the cell's front door, they will bind a sodium ion and a glucose molecule at the exact same time.
So the sodium moving downhill into the cell provides the physical momentum to drag the glucose uphill against its own gradient.
Yeah, it acts just like a water wheel.
I like that analogy.
Right. The energy of the water flowing downhill turns the wheel to grind the wheat. In this case, the sodium flow powers cotransporters, like SGLT2 and SGLT1, to pull glucose back into the body.
And amino acids, do they use this too?
They do. Amino acids are retrieved using a very similar cotransport mechanism.
Okay, but if there's a physical transport maximum, it becomes a sheer capacity issue, right?
Absolutely. We're talking about actual molecular machines embedded in the cell membrane.
They don't just hold an open door. They physically have to bind to the glucose, change their protein shape to move it across the membrane, release it, and then completely reset.
Yeah, and that mechanical process takes time. A fraction of a millisecond, but it takes time.
So if you multiply that, there has to be a hard limit to how many molecules can be processed per minute, no matter how much glucose is waiting out in the tube.
Right. When the tubular load exceeds the physical binding speed of those proteins, saturation occurs. Like bouncers at a club door getting totally overwhelmed by a crowd.
Yeah, the bouncers just can't check IDs fast enough.
Exactly. The normal transport maximum for glucose in an adult is roughly 375 milligrams per minute.
So what happens if you exceed that, like in the real-world scenario?
Well, look at a condition like uncontrolled diabetes mellitus. Plasma glucose gets so high that the filtered load vastly exceeds what those carrier proteins can process.
The bouncers are overwhelmed.
Completely, and the remaining glucose simply has nowhere to go but down the assembly line, eventually spilling out into the urine.
Which makes sense. And speaking of this assembly line, it is highly compartmentalized.
Oh, very much so.
The fluid doesn't just flow through a uniform hose. It hits highly specialized stations, starting with the proximal tubule right after the glomerulus.
Yeah, the proximal tubule is the heavy lifter of the whole system.
Because it does most of the initial work.
Yeah. Its cells are packed with mitochondria to power all those active transport pumps we talked about, and the extensive brush border multiplies the functional surface area 20-fold.
That is massive.
It is. This first station alone reabsorbs 65% of the filtered sodium and water. And it completely clears out 100% of the glucose and amino acids.
And it even engages in protein eating, right? I read this in the source text and it blew my mind.
Oh, pinocytosis. Yeah, it's amazing.
Right. If large proteins accidentally slip through the initial filtration, the proximal tubule uses pinocytosis. The cell membrane physically invaginates, creating this little pocket that swallows the protein whole.
Just gulps it down.
Yeah, pinching off into a vesicle.
Yeah.
Once it pulls the protein inside, it uses lysosomes to digest it down into basic amino acids and just ships them right back to the blood.
It's an incredible salvaging operation. But moving past the proximal tubule, the fluid plunges down into the renal medulla through the loop of Henle.
Okay, the loop of Henle, this is where things get kind of weird, architecturally speaking.
Definitely. This loop has a descending limb that dips deep into the kidney, a sharp hairpin turn, and then an ascending limb that comes back up.
And the rules change at every station. The cellular structures of these two sides are fundamentally opposed.
Exactly. The thin descending limb is highly permeable to water.
So water can just leave.
Yeah, as the fluid travels down, water freely diffuses out into the surrounding medullary tissue.
But as soon as it rounds the corner and becomes the thick ascending limb, the architecture completely changes. The cell membranes become virtually waterproof.
Which is such a drastic shift.
It is. The water that is left inside the tube is certainly trapped. It can't get out.
Right. And while locking the water inside, The thick ascending limb starts aggressively pumping out solutes.
How does it do that?
It utilizes a massive cotransporter called NKCC2. This pump moves one sodium, two chlorides, and one potassium ion from the tubule fluid into the cell.
Okay, so by stripping the solutes out but leaving the water trapped inside, the fluid inside the tubule actually becomes heavily diluted.
Exactly. It's diluting the fluid, but there's also a crucial electrical quirk happening here.
Oh, right, the positive charge thing.
Yeah. A portion of that pumped potassium actually leaks back out into the lumen.
And potassium is positive.
Right. So this leak creates a slight positive electrical charge of about positive 8 millivolts in the tubular fluid.
Okay, and a positive charge in a confined space is going to repel other positive ions.
Basic physics.
Yeah, so that slight 8 millivolt charge physically pushes vital positively charged minerals, specifically things like magnesium and calcium, out of the tubule.
It forces them to squeeze between the cells and back into the bloodstream. It's a very clever way to reabsorb those minerals without spending extra energy.
The source text mentions specific drugs that act right here, too.
Oh, yes. This specific region is the direct target for powerful loop diuretics.
Drugs like furosemide, right?
Exactly. Furosemide or ethacrynic acid. They work by chemically blocking that NKCC2 cotransporter.
So if you disable the pump, the sodium, chloride, and potassium just stay trapped in the tubule.
Yeah, and because the solutes are trapped, the water stays locked in with them due to osmosis.
Which means the patient ends up excreting a massive volume of fluid.
Exactly. That's why they're such potent diuretics.
Okay, so past the loop of Henle, we enter the distal and collecting tubules.
Right. And if the proximal tubule is the heavy lifter, these later segments are the precision fine-tuners.
They're adjusting the final details.
Yeah, largely thanks to the intercalated cells. They basically manage systemic acid-base balance by acting as a toggling cellular thermostat.
That's fascinating. How does the toggle work?
Well, during systemic acidosis, when your blood is too acidic, your type A intercalated cells spin up specialized hydrogen ATPase pumps.
As these pumps secrete acid.
Right. They can actively secrete hydrogen ions into the urine against an absolutely brutal concentration gradient of up to 1,000 to 1.
Wow, 1,000 to 1.
Yeah. And for every hydrogen ion they blast out of the body, they synthesize and absorb a bicarbonate ion back into the blood to buffer the acidity.
So what happens if the blood is too alkaline?
Then the type B cells handle the opposite scenario. During alkalosis, they use a transporter called pendrin to literally reverse the flow.
So they secrete the bicarbonate into the urine and reabsorb hydrogen instead.
Exactly. It's a perfect dual system.
But, an assembly line capable of toggling acid, dumping water, or saving salt is totally useless without a management system.
Right. The kidneys need constant, real-time data on systemic conditions to know what to do on any given day.
Blood pressure acts as a foundational physical signal here.
Right, it does. The peritubular capillaries, those are the blood vessels wrapping around these tubules, they maintain a net reabsorption force of 10 millimeters of mercury.
Which is basically a localized vacuum. It's constantly sucking the fluid that the tubular cells push out their back doors into the bloodstream.
Yeah, a 10 millimeter mercury vacuum. And the strength of that vacuum is dictated by resistance and pressure, which brings us to the hormonal managers.
The bosses of the system.
Exactly. The body uses chemical signals to alter both the physical vacuum and the cellular pumps. Let's start with aldosterone.
Secreted by the adrenal cortex.
Right. It targets the principal cells in the late distal and cortical collecting tubules. Its primary directive is sodium conservation.
So it tells the kidneys to save salt.
Basically, it enters the cell and actually alters genetic transcription to literally manufacture more sodium-potassium pumps and insert more sodium channels into the cell membrane.
Here's where it gets really interesting, though. When we look at systemic crisis management, like a severe drop in blood volume or blood pressure from hemorrhage, or say extreme dehydration, angiotensin II takes over.
Oh yeah, angiotensin II is the big one. It's the body's most powerful sodium-retaining hormone.
Because it hits the problem from multiple angles simultaneously.
Yeah, exactly. It acts systemically to stimulate aldosterone, but locally within the kidney, it directly upregulates the sodium-hydrogen exchange pumps in the proximal tubule.
So it's revving up the pumps.
Yes, but even more critically, it acts on the blood vessels themselves. Specifically, it constricts the efferent arterioles.
The exit tubes leading away from the glomerulus. So by pinching off the exit, blood pressure builds up upstream in the glomerulus to maintain filtration.
Oh.
but the pressure plummets downstream in the peritubular capillaries.
And that pressure drop is everything. Dropping the capillary pressure turns up the power on that localized vacuum.
So it sucks vast amounts of sodium and water out of the tissues and back into the circulatory system to save your blood pressure.
Exactly. It's a brilliantly coordinated crisis response.
What about just pure water conservation? Like if you're just dehydrated but your blood pressure is okay.
That is primarily managed by ADH, the antidiuretic hormone.
How does that one work?
Well, when osmoreceptors in the brain detect that your blood is becoming too concentrated, the pituitary releases ADH. When ADH reaches the collecting ducts in the kidneys, it binds to receptors and triggers a stunning mechanical response.
The aquaporins.
Yes. The cells take vesicles packed with these specialized proteins called aquaporin 2, and they rapidly shuttle them to the apical membrane.
The vesicles fuse with the membrane and the aquaporins just snap into place, creating instant open water channels.
It happens so fast. A section of the tubule that was completely waterproof just a minute ago is suddenly highly permeable.
So water rushes out of the tubule and back into the hypertonic medullary tissue.
Right, saving the water. And without ADH, those aquaporins just stay hidden inside the cell, the wall stays waterproof, and you get a condition called diabetes insipidus.
Where a patient might excrete up to 20 liters of highly dilute urine a day because they literally can't save the water.
Exactly, it's a massive leak. But the system also requires a counterbalance for the opposite extreme, fluid overload.
Like if you eat a really salty bag of chips and drink a gallon of water?
Yeah, if your blood volume expands too much, the physical stretching of your heart's atria triggers the release of atrial natriuretic peptide, or ANP.
So the heart tells the kidney what to do.
Basically, ANP travels to the kidney and directly inhibits sodium and water reabsorption in the collecting ducts.
It overrides the conservation signals.
Exactly. It forces the kidneys to dump the excess sodium and water and bring blood volume back down to a safe baseline.
Okay, so with all these overlapping systems, we have active pumps, concentration gradients, all these hormonal toggles. How do doctors actually know if the factory is hitting its quotas?
That's the real clinical challenge.
We need a tracking metric, which leads us to the concept of clearance.
Right, renal clearance. It is defined as the volume of plasma that is completely cleared of a specific substance by the kidneys per unit of time.
It's the report card for the kidney.
Exactly. It provides a mathematical window into the glomerular filtration rate, or GFR. But to measure GFR accurately, you need a substance that is freely filtered by the glomerulus, but completely ignored by the rest of the tubule.
Meaning it's never reabsorbed and never secreted.
Right. And the absolute gold standard for this is inulin.
Which is a plant polysaccharide.
Yes, derived from plants.
But wait, if inulin is a plant polysaccharide, our bodies don't naturally produce it.
No, they don't.
So relying on a continuous IV infusion of a plant extract for every routine kidney checkup seems wildly impractical. There must be an endogenous substitute, right? Like a built-in tracking tag.
Yeah, clinical medicine couldn't survive doing inulin infusions all day, so we rely on creatinine for exactly that reason.
Creatinine is a natural muscle byproduct, right?
Yes, a constant byproduct of your own muscle metabolism. And like inulin, it is almost completely filtered and rarely reabsorbed. This creates a vital, highly sensitive diagnostic seesaw.
A seesaw? How so?
Well, if a patient experiences kidney damage and their GFR drops by 50%, their kidneys are suddenly filtering half as much creatinine.
So the creatinine backs up in the bloodstream.
Right, until the plasma concentration exactly doubles.
Ah. And at that doubled concentration, even a damaged filter operating at half capacity will push the normal amount of creatinine through, reaching a new steady state.
Exactly. The math balances out. So a simple blood draw showing doubled creatinine instantly tells a doctor the patient's filtration rate has been cut in half.
That's incredibly elegant. What about measuring total renal plasma flow, though?
For that other major parameter, doctors use a synthesized acid called PAH, or para-aminohippuric acid.
Because it behaves differently than creatinine?
Very differently. PAH is unique because the tubules actively secrete it so efficiently that roughly 90% of it is cleared from the plasma in a single pass through the kidneys.
Wow, 90% in one pass.
Yeah. So by measuring PAH clearance, we can calculate the exact volume of blood flowing through the entire renal system.
So what does this all mean? When you strip away the specific protein names and the complex clearance math, you realize your kidneys are not just passive strainers catching debris.
No, they are incredibly dynamic, energy-hungry recycling centers.
They utilize this massive network of pressure gradients, molecular locks and keys, and hormonal feedback loops to meticulously balance your internal ocean molecule by molecule.
All while continuously throwing out the metabolic trash.
It's unbelievable.
It is. And, that meticulous efficiency actually brings up a really profound tension between our biology and modern medicine.
Specifically regarding the tubular secretion part we were just talking about.
Exactly, because the proximal tubules have evolved to be unbelievably efficient at recognizing foreign substances and rapidly secreting them into the urine.
To protect you from toxins in the environment.
Right. The problem is your kidneys don't differentiate between a deadly plant alkaloid and a life-saving pharmaceutical.
Oh, wow. I didn't even think about that.
Yeah. The tubular secretion system clears drugs like penicillin and salicylates so aggressively that it creates a massive clinical hurdle just to maintain a therapeutic dose in a patient's bloodstream.
So the very evolutionary mechanism that has kept humans alive for millennia is actively working overtime to pee out your vital antibiotics.
The ultimate biological irony. Your body fights the medication simply because its internal security system is too good at its job.
That is wild. Definitely keep that in mind the next time you take a prescription. Just think about the entire contents of your house being emptied onto the front lawn, the precise cellular bouncers checking molecular IDs, and the aquaporin channels snapping into place to keep you hydrated. Take a moment to appreciate your internal microscopic recycling plants today. Thanks for joining us, and we'll catch you on the next Deep Dive.